Okay, you wanted videos? Here's some videos. First step, let's make some membrane potentials. Okay, this is a little bit more in depth than I went into into class the other day because I'm going to potentially be able to use this for AMP1 or AMP2 because the result is the same. If we have an electrically charged cell, we have different types of membrane potentials. You have a resting potential. The resting potential is the battery. This is the charged membrane, the ability to be able to generate electricity. That's on, we'll call this on one end of the spectrum. We're gonna call this the battery, right? And remember, a battery basically has a positive and a negative terminal, and you connect the two sides. And that's how you end up with, over on the other end, the action potential. You connect those two sides, you end up with electricity. And then in the middle, you have graded potentials. Okay, all of this is based on the normal membrane of the cell. Okay, we're gonna have extracellular side, intracellular side. And what we have to create is a battery at rest where there's a positive terminal outside of the cell and a negative terminal inside the cell. And the way we do that is we have to look at the chemicals that exist around the membrane and their normal distributions that are created by the portions, by the channels that are in the membrane itself. Okay, so the first couple of channels that we're going to pay attention to are going to be leak channels. And in red here, we're going to have the sodium leak channel. And then let me find another color here in pink. This is going to be the potassium leak channel. What you want to picture is where would our normal distribution be to begin with, okay? So our positive terminal would be sodium outside the cell, and then we would have potassium built up inside the cell. And one of the things, this is where students like to say this is a trick question. So what creates the positive terminal? The sodium outside the cell, right? Positive, positive. What creates the negative terminal? Everyone wants to say potassium, except guess what? Potassium has a positive charge, can't be a negative terminal. What actually provides the negative terminal are large anion proteins. That up in the screen. Now the benefit is sodium, potassium will move through these leak channels, but the anion proteins are going nowhere. Now I also created kind of a color code scheme for types of gradients, electrical and chemical gradients. Chemical gradient is where you have a large concentration of a chemical in one area and a smaller concentration in another area. So for example, we have a large concentration of sodium outside of the cell compared to inside the cell. So there is a chemical gradient for sodium towards the inside of the cell. So what we should expect is that sodium wants to leak into the cell. For potassium then, there is an opposing chemical gradient towards the outside of the cell. We have a large concentration of potassium inside the cell compared to outside the cell. And so we should expect to see potassium leak through that potassium channel. Now, we can't pay attention to just the chemical gradient because there's also an electrical gradient. Electrical gradient is a little simpler. So a gradient is where you have a difference. So an electrical gradient would be an electrical difference. So you have a positively charged sodium outside the cell and you have a negative charge inside the cell. So for sodium, in addition to there being an electrical gradient, there is a chemical gradient pulling sodium towards the inside of the cell. For potassium, however, the outside of the cell is positively charged, so that's actually going to repel the potassium. Potassium is going to be more attracted to these negative anion proteins, so you kind of have this opposing electrical gradient for sodium that's kind of drawing it towards the inside of the cell. Now, not pictured in this little spot is that there's also a sodium-potassium pump. Pump means it requires ATP. Whenever we see energy going into the transport can be in either way, but likely the reason that we're putting energy in is because we're transporting something up its gradient. So for example, sodium is getting kicked out of the cell and potassium is being dragged into the cell. Now, just real quick, these leak channels aren't created equal. The sodium leak channels, sorry, get my finger right here, the sodium leak channel is much slower than the potassium leak channel. So we end up at resting potential at the point where potassium hits its electrochemical opposites. So essentially, there's a chemical gradient forcing potassium out of the cell, but there's a chemical gradient pulling it back towards the center of the cell. We end up at a point where it's slightly negative inside the cell and potassium is trapped. The pull of the electrical gradient holds it from going down its chemical gradient. If one sodium were to come in and add one positive charge to the inside of the cell, that would allow one potassium to pop back out, and then we're right back where we started because the sodium-potassium pump is going to reset that. So that's the resting potential.